Hello, everyone. My name is Rohan Shah, and I'm going to be the MC for this session on by Stuart Russell. So I'm excited to introduce you to him. I know Stuart best as my advisor when I was doing my PhD at the Center for Human Compatible AI. But of course, he also has a real academic bio. Stuart is a professor of computer science at the University of California at Berkeley, holder of the Smith-Zadeh Chair in Engineering, and director of the Center for Human Compatible AI. He is a recipient of the IJCAI Computers and Thought Award, and from 2012 to 2014, held the Chaire Blaise Pascal in Paris. His book, Artificial Intelligence, A Modern Approach, with Peter Norvig, is a standard text in AI, used in 1,500 universities in 135 countries. He is also author of Human Compatible. His research covers a wide range of topics in artificial intelligence, with an emphasis on the long-term future of artificial intelligence and its relation to humanity. He has developed a new global seismic monitoring system for the Nuclear Test Ban Treaty and is currently working to ban lethal autonomous weapons. Today, Stuart will be discussing the problem of creating provably beneficial artificial intelligence, arguing that the standard model for developing AI poses major risks. We invite you to use the SwapCard platform during this session. On the right side panel, feel free to share your thoughts on the live discussion board and leave and upvote any questions for our speaker to answer at the end of the presentation. After the session, we invite you to use SwapCard to set up meetings with fellow conference attendees. Stuart will also be hanging around afterwards to answer questions on GatherTown. Without further ado, welcome, Stuart.
Thank you very much, Rohan. So Rohan gave a pretty good summary of what I'm going to say. I understand that this is a broad audience interested in all kinds of risks. So let me first of all explain about AI. So of course, AI is about making intelligent machines. The question is, what does that mean? And historically, what it's meant, and I'm going to refer to this as the standard model, is making machines that are intelligent to the extent that their actions can be expected to achieve their objectives. And this borrows the standard notion of rational behavior from philosophy and economics, where it was developed over several centuries. AI has lots of subfields: problem solving, the kinds of algorithms that get you to the airport when you use your GPS navigation system, game playing, the kind of program that beats human world champions, knowledge representation, reasoning, planning to allow a system that knows something to convert knowledge into action, natural language processing, speech, vision, robotics. These are all obvious. And then machine learning is the thing that's mostly in the news these days. It's actually been around for a long time. In fact, in 1950, Alan Turing recommended machine learning as the most likely route to build human-level intelligent systems. So, as you know, it's a huge field. There are tens or perhaps hundreds of billions of dollars being invested into developing, improving AI. And it's a very rapidly growing field. There's enormous demand for it. Little factoid, I think almost 2/3 of all applications to our entire department in Berkeley are specifically to study artificial intelligence. So given all this amazing level of energy and effort, what happens if we succeed in our goals? Well, we can go back and ask Alan Turing. Here he is. And in 1950, he was pretty optimistic. He talked about the prospects for all kinds of things that you could do with AI and how wonderful it would be. By 1951, he was talking on the radio and he said, it seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So there it is, right? No mitigation, no solution, no apology, just resignation. This is the future of mankind. So fast forward 70 years, and we're starting to see some of the technology existing. We have self-driving cars. We have programs that can beat human world champions at really complicated games like Go. And we're also starting to see some of the downsides. Racial and gender bias in algorithms, the expansion of disinformation, the impersonation of human beings. So I'll ask you guys later, which of these four is actually a real person? Using AI systems to kill people, replacing human roles in the economy with machines. But there's also an upside, right? There's a reason why we're spending all this time and energy and effort to create AI. It's not just for the fun of it, and it's not just, as Lord Lighthill said in his 1973 report, that it's a bunch of male scientists who are unable to have children, and therefore they want to create AI instead. It's actually because AI can have enormous benefits. So to illustrate what kind of benefits it could have, we could actually sort of go back in history and say, what was it like getting to Australia in 1800? Well, it would take you hundreds, maybe even thousands of people, a fairly hefty project to outfit a major expedition, probably take you about 10 years start to finish, and you'd probably be dead before you got there. But now, because of the advance of technology, we have what you might call travel as a service, right? It's just as we have electricity as a service, water as a service, we have travel as a service. You take out your phone, you go tap, 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 and you can be in Australia tomorrow. And it costs you not $1 billion, but $1,000, or in other words, it's basically free in relative terms. And you're going to be alive when you get there. That's if they let you in. So what human-level AI promises is that kind of improvement in everything. So XaaS means everything as a service. And we can expect the same type of cost reduction, not necessarily the same speed improvement, because there are limits in physics and biology and also in the human mind. But we can eliminate cost and essentially use AI as a source of wealth. So if you wanted to run this conference in 2035, you would just ask your laptop to do it, and it would take care of it. It would set up everything. It would invite all the right people. It would make sure that the environment was great, that everyone was meeting each other, and it would be wonderful. If you're in some remote village where you don't have access to government services, you can just ask the AI systems to come along and build some houses and schools and maybe a road connecting you to the nearest city, and teach your children, and if you need surgeons, perhaps train the surgeons as well, or even be the surgeons. And you shouldn't think of AI, the kind of AI that will be doing this, as individual robots. Most media portrayals and movie portrayals have the AI embodied in a single physical object, but it's going to be, as people say now, in the cloud. It'll be a globally connected, essentially a single system, and it will have physical extensions that it can deploy whenever they're necessary, and they will have whatever physical characteristics are necessary, whether it's for operating inside a house, or moving at high speed with wings, or carrying enormous loads with wheels, and it will carry out essentially whatever tasks we know how to do, and perhaps even some that we don't. And so in a very conservative forecast of what we could do with this kind of technology, not inventing cures to new cures to diseases, or faster than light travel, or life extension, or these sort of other sci-fi things, but just things we already know how to do, but just doing them effectively, efficiently, and at almost zero cost. We could lift the living standards of everyone on Earth to a respectable level. At least, well, Ted Parson, the previous speaker, is probably going to disagree with that because we might not have the resources to do so. But let's say that we do this efficiently. It's about a tenfold increase in the GDP of the world, which is about a $13.5 quadrillion net present value. So the cash equivalent of the increase in global income would be about $13.5 quadrillion. So that's a lot of money. And it makes the tens or hundreds of billions of dollars that we're investing absolutely negligible in comparison, right? We're not even, it's like spending a penny to buy a house. And if this technology becomes available, I think it would have some globally beneficial effects on the way we relate to each other, because there should at that point be no need for conflict over wealth, because everyone would simply be able to make more of it when they need it. Just as you can make more digital copies of a newspaper, and so we don't fight over who has more digital copies of the Financial Times, because if you want another one, you can just make another one. So I think we have to accept that AI systems are going to be more capable than humans in the future of making decisions in the real world, not just on the go board. But if we gradually relax through research advances, we relax the assumptions that may go easy, such as complete observability of the state of the world, completely predictable rules, discrete state, and so on. We can relax these technical assumptions by developing more powerful algorithms. And eventually we have systems that can outthink us in the real world. And what Turing is asking is, okay, if you do that, then you have systems that are more powerful than human beings, because our decision-making capacity is what gives us power over the world. So if you're making entities more powerful than ourselves, how are you going to retain power over them forever? And Turing obviously sees no answer to this question. And that's why he's resigned to a future in which machines take control. Now, it seems reasonable actually to ask, is there any way out, right? Short of banning AI altogether. And Turing actually went on to refer to Butler's book, Erewhon, in which they have banned machines for exactly this reason. And for those of you who've read Dune, you know that there was a Butlerian jihad, so that refers back to Butler. And this jihad was to destroy all machines. And they added another religious commandment saying, thou shalt not make a machine in the likeness of man. So they don't have computers in Dune, because as soon as you start having computers, you start making them more intelligent and you go down the slippery slope and you almost lose control, as happened in Dune. So I actually think that it's not as bad as that. I think there is a way that we can avoid the fate that Turing is predicting by understanding where things are likely to go wrong. And one source of the problem is in the standard model of AI, the one that I talked about earlier. And it's not just AI, right? This same approach where we design machines that optimize a fixed specified objective on our behalf. That's what happens in control theory, where you minimize the cost function. In statistics, you minimize a loss function. In operations research, you maximize a sum of rewards. In economics, you maximize GDP or utility or social welfare. So this is a pretty powerful and pretty widespread model for how to do things. But it's a mistake, because once we get outside the lab or narrowly constrained systems, we don't know how to specify objectives completely and correctly. So a simple example, the self-driving car companies right now are trying to figure out what the objective is that their car should be maximizing. And it's still subject to revision, and they're constantly finding places where they need to fix it up. And that's for a system that can only move a steering wheel and the gas pedal and the brake pedal, right? It doesn't have access to a keyboard or anything like that. And so it's very restricted. Now we've known this point about the difficulty of specifying objectives completely and correctly for thousands of years. And almost every culture has legends like this or myths like this, where here's King Midas, and King Midas specified the objective: everything I touch should turn to gold, and his objective was granted. The gods being the gods, they gave him exactly what he asked for. So there, the gods were playing the role of the AI system. And then, of course, his food and his drink and his family all turn to gold. And he dies in some versions in misery and starvation. In Goethe's story, The Sorcerer's Apprentice, right, the apprentice asks the brooms to fetch water, but he forgets to say how much water. And then, of course, the whole house fills up with water and the sorcerer has to intervene. And if you ever get one of these magic lamps where the genie grants you 3 wishes, in those stories, typically the 3rd wish is, please undo the first 2 wishes because I made a mess of the universe. But what happens if we don't even get a 2nd wish, right? So the literature on AI safety is full of examples of ways that things could go wrong. You want to restore carbon dioxide levels in the atmosphere, and the system does so perfectly successfully in a way that wouldn't make Ted Parsons happy, because it reduces the level of oxygen in the atmosphere by 25%, and we all slowly die of asphyxiation, et cetera, right? And Max Tegmark's book, Life 3.0, has a very nice, I guess it's a prologue or preface, which describes at great length a process by which, with the cooperation of human beings, a super intelligent machine gradually takes over our entire planet. So if we follow the standard model of AI and we specify an incorrect objective, then we are actually kind of setting up a chess match between us and the machine, right? Because we've got us with our actual objectives, and then we've got a machine with a different objective. And if that machine is more powerful than us and it's pursuing this objective, which is misaligned, and it could be, we could think of it as one machine, or you could think of it as some globally distributed system that's set up to optimize a given objective. Then basically we don't want to be in that chess match. And I think it's actually starting to happen. One example is what's happening in social media, where the algorithms are set up with an objective, which is something like maximizing click-through or engagement or various other measures that appear to actually align the interests of the user, who wants interesting things to read and look at, and the company, who wants clicks, because clicks generate revenue. And so I think when this was designed initially, the idea was that the algorithms would learn what people want, what they're interested in, and we send it to them. And that sounds okay. And people started to talk about the filter bubble, that, of course, if it only sends things you're interested in, you stop learning about things that are outside your bubble, and perhaps your interests gradually narrow over time. But actually, this isn't what happens. When you ask a learning algorithm to maximize click-through, what it does is it comes up with ways to manipulate people through the sequence of content that it sends you, so that in future you are more predictable. Because the more predictable you are, the more it can maximize click-through. And so it doesn't want to leave you the way you are, where you're unpredictable and you have wide interests. It actually wants to change you into a more predictable and typically more extreme version of yourself in order to monetize you. And I think many people argue that this is one of the major ills affecting society today. And you can see that these are very simple algorithms having already a massive global effect because of the way they're deployed on billions of screens. If they were better algorithms, if they were actually able to think about your interests rather than just treat you as a clickstream, then they could do far more damage. And if you imagine that the AI system also gets better at generating content that is able to manipulate you, then the outcome could be far worse. And this is a general property of AI systems built in the standard model, that if they're pursuing an incorrectly defined objective, they will be better able to achieve it. They will be better able to mess with the parts of the world that are not mentioned in the objective in order to optimize the achievement of the objective and the probability of success. And they will be better able to prevent humans from interfering with that process. So it looks like this is a methodology where success means failure. And that's a good sign that the methodology is probably the wrong one. And I think the story, and this is sort of a very, very simple historical reconstruction of why we got into it, is because when we were setting up the field of AI in the 40s and 50s, it was natural to think, okay, what do we know about humans that makes them intelligent? What is our sort of scientific definition of intelligence in humans? And one version of it was the sort of psychological or cognitive science definition, that just said, let's copy actual human cognitive processes. But the one that won out in the field of AI is let's build AI systems that are rational, because that's a scientifically definable or mathematically definable notion that we can actually constructively pursue. So we took that definition of intelligence in humans and we just copied it to machines. And I'm arguing that that was a mistake. So what should we do instead? Well, the problem with this definition is that we are not able to transfer our objectives correctly and completely into the machines. If we could, I wouldn't be too worried about this. But since we can't do it, then we're stuck with something else, right? We're stuck with making machines that are beneficial to the extent that their actions can be expected to achieve our objectives. And so our objectives are going to remain in us, but the machines have to be beneficial to us according to those objectives. And this is almost a truism, that this is in fact the type of machine that we should build, right? It is rational for us to build machines of this type and not of the other type. And we can turn that simple idea into some principles, 3 principles, because it's, maybe it's Isaac Asimov's birthday or something, but the 3 principles are, first, that the machine's only objective is the satisfaction of human preferences. And I'm using preferences here in the same sense as von Neumann and Morgenstern, meaning you're ranking over all possible futures, or in fact, over lotteries over all possible futures, not just what kind of pizza you like, but your preferences about the entire future. But the second principle says that the machine does not know what those preferences are. And this uncertainty turns out to be crucial. The third principle provides a kind of a grounding for this whole notion of preferences that connects humans to machines. And how is the machine going to find out anything about what our preferences actually are? The answer is from human behavior, right? That is the primary source of evidence about human preferences. There could be other things, for example, direct fMRI measurements, and that way you could actually get preference information from locked-in patients, for example, which might be helpful. But in general, it's going to be from human behavior, or obviously the consequences of human behavior. So you can take those three principles, you can formulate them as in a mathematical framework, which we call assistance games. So it's a game because there are at least two decision-making entities, and economists call decision problems with more than one entity games. There's at least one human, at least one machine. It's an assistance game because the whole purpose of one of the entities, namely the machine, is to be of assistance to the other entity. These assistance games have a lot of interesting structure. I'm not going to go into any mathematical stuff here because of the nature of the event and the audience. I'm happy to do that in GatherTown afterwards. But when we solve these games, and we've actually solved a few of them, simple ones, but we can look at the solutions and understand the properties of the behavior that is exhibited by a machine that is solving this type of game. And we find that it will defer to the human. It has an incentive to ask permission before doing anything that would impinge on aspects of human preferences that it doesn't know. Right? So, for example, if it knows that we want to restore carbon dioxide levels to the proper amount, but it doesn't know how much oxygen we want in the atmosphere, and it comes up with a plan that changes the amount of oxygen, then it has an incentive to ask our preferences about oxygen levels. Okay, and it won't do anything before finding out enough about those preferences to be pretty sure or almost completely certain that its plan is something that's acceptable to humans or preferred by humans. And crucially, it allows itself to be switched off, which is not true of AI systems that are built in the standard model. So I'll talk about that in a minute. And as I mentioned, we can show that it's rational for humans to build machines that solve assistance games. If we were able to write down our preferences completely incorrectly and put them in machines, it would be rational for us to build machines in the standard model. But we cannot, and it's not rational for us to build machines in the standard model. But I believe it is rational for us to build machines within this model. And in this model, it fixes what seems to be wrong with the standard model in the sense that as the AI system becomes more and more capable, it becomes better at learning about our preferences and better at satisfying our preferences. And so we get better outcomes. So let me just illustrate this off switch problem that I mentioned. Right, here's our robot. There's the off switch on the back. And this is the big, heavy robot. It's about 400 pounds. And that's why it has an off switch. And in the classical way, the standard model for AI, right, if you give it an objective like fetch the coffee, right, that becomes its life's mission, right? And it doesn't take a genius to figure out that you can't fetch the coffee if you're dead. And so the robot instantly, as a result of being given an objective that is not easy to achieve when dead, now has an incentive to preserve its own existence. So this is not built in. This is simply a consequence of being given the objective in the first place. And so since it wants to avoid death, one way to do that is to disable its off switch and possibly take other preemptive measures to stop any interference with this mission of fetching the coffee. So this is what we want to avoid, right? We want systems that do allow themselves to be switched off. So when the machine is uncertain about the objective, so it might know that I prefer to have some coffee now, but it may know very little actually about the rest of my preferences. So the thinking goes quite differently. The human might switch me off, but only if I'm doing something wrong, right? And the point here is the machine doesn't know what wrong means, right? So it doesn't know which of our preferences it might violate, but it doesn't want to violate any of them. And so it has an incentive to allow itself to be switched off in order to prevent preference violation, right? The first principle is basically telling it, the dual of the first principle is avoid preference violation, right? And so it has a quantitative incentive to allow itself to be switched off. And you can actually very simply prove this as a theorem by writing everything down in Greek. And then you get a theorem that the robot is provably beneficial and provably has a positive incentive to allow itself to be switched off as long as it remains uncertain about the human preference model. And when that uncertainty goes away, the incentive to allow itself to be switched off also goes away. So I promise not to go into a lot of math, but I want to just head off a lot of misunderstandings, so we don't waste a lot of time in the Q&A. I'll ask some of these questions and then I'll answer them right now. So a common response I get is, well, who are you, you white, cisgender, Episcopalian, affluent Western male, to determine the values that AI systems are going to be optimizing, or are you going to build in Christian values, or all kinds of variants of the same basic idea that we're building in a set of values into the machine for it to optimize. And the answer is no. We're not building in one set of values at all. In some sense, there's no set of values beyond that the machine is there to be of benefit to humans. And it will have potentially, if there are 8 billion people, 8 billion different preference models about what the future should be like. Another question is, won't the robot learn from bad humans to behave badly? And the answer is no. No more than a criminologist learns to be a criminal by observing criminals. So bad people, or people we think of as bad because they do actions that are harmful to others, they have their preferences. And the only exception to this rule is the pure sadist, right? The one who takes actions that cause harm to others simply in order to derive pleasure from the harm inflicted, right? Harming others in order to, obtain money, in order to, buy yourself a catamaran, right? That's a motivation, and one can separate out the positive preferences that the agent has, what they want in life, from the negative effects on others. And the AI system won't help the human inflict negative effects on others, because that's not what it does. But we do need to zero out the sadistic preferences of humans. And this is a long discussion in the theory of utilitarianism. And there seems to be a pretty good consensus that that's one way of treating it. In machine learning and reinforcement learning, there's a whole subfield called imitation learning, where humans do things and then machines try to copy them. It might be gymnastics or walking or anything like that. So some people get confused and think that, well, this, because I'm putting a machine and a human in the room together, and the human is going to be demonstrating something, the machine's going to copy it. No, not at all. It's not the same. And just to give you two examples, right? If the human in the room drinks coffee, right? I don't want the machine to drink coffee, right? That's not the goal here, right? In fact, what should happen is that the machine, at the appropriate time, fetches the human some coffee to drink, or help, brings it to them in bed in the morning or whatever it might be. Similarly, if the human says, I would like a cup of coffee, right? We don't want the machine to say, I would like a cup of coffee, right? That's what imitation learning would do, and that's completely not what we're setting up here. So there is some, family resemblance to imitation learning, but it's actually a completely different problem. Some people argue that this approach can only work if people are doing just zillions of demonstrations all the time for everything that they ever want the machine to do. And the answer is no. In fact, they might not have to do any demonstrations at all. And part of Rohin's thesis was actually showing that you can learn a great deal about human preferences simply by observing the state of the world. And we call this, or I call it, the non-naturalistic non-fallacy, because the world is not sampled from a state of nature, right? The world is the result of the actions of billions of humans operating on their preferences. And so by looking at the world, we can learn a lot about what those preferences must have been for all those people to do all those things that resulted in the present state of the world. So you might not have to have any demonstrations. You can also read all the books that humans have ever written, watch all the movies, and learn tons and tons and tons of stuff. And babies do this all the time, right? I mean, each human has learned their own set of preferences from a relatively small amount of experience. And a lot of it, I think, is actually explaining why the other humans around them are doing the things that they're doing. Some people, mathematically oriented, think, well, okay, if there's uncertainty over the preferences, well, why don't you just, take expectations, integrate it out? And that's correct, actually, if it's not possible to obtain any further information about human preferences. And this is a result going back to the early 1970s, showing that, MDPs with uncertainty about the reward function can simply be converted into regular MDP by integrating out the uncertainty on the reward function. And then there's an extension of that where additional observations can tell you more about the reward function. And when that's the case, then you get a different policy, sort of obviously, right? So if preference information can flow at runtime from the human to the machine, then this idea of integrating out the uncertainty is not correct, right? The theorem fails, and the machine behaves in very, very different ways when it's possible to gain more information about preferences. So that's a no. And lastly, a lot of people think that assistance games are requiring the machine to learn about human preferences. Nothing in the formulation says that, right? And in fact, we can have machines that simply optimize a policy over time, right? So they're not learning anything about preferences, they're just tweaking a policy, gradually changing it over time, and we can show that in the limit of enough experience, that machine is doing exactly what it should do if it's going to be solving the assistance game. Okay, so it doesn't have to be explicitly learning preferences any more than something that, an agent that satisfies the von Neumann-Morgenstern axioms has to actually have a utility function, right? It doesn't, it just has to act as if it did. Okay, and there are all kinds of ways to do that. In fact, pretty much all of the methods we use in AI are based on doing von Neumann-Morgenstern implicitly. So the answer to that is no. There are lots of other questions that I don't really yet have answers to. And I'm just going to very quickly run over those. So first of all, the basic theory that I've outlined here initially talks about results obtained with one machine and one human. Obviously, there's more than one human. And the problem there is not that the humans have different preference models. That's fine. We'll just learn billions of preference models, just like Facebook does. The problem is mainly, how do you make trade-offs among the preferences of many different humans? I think most people in AI naturally gravitate to a utilitarian approach to this problem. And in the book Human Incompatible, I argue that, in fact, many of the objections to that approach don't really hold up. I'm not saying that there are no possible objections, but most of them seem to be quite manageable. But these are questions that moral philosophers and economists have worked on for hundreds or thousands of years. And there are still many open questions in formulating the basic theory. For example, how do you make decisions when the effects of your actions can change the number of people who exist? How do you make decisions on behalf of humans whose preferences change over time? right? These are fundamental philosophical questions that we don't have answers to, but need answers if we're going to flesh out this approach. We also have to be concerned about what happens when there are many machines doing this, particularly machines that are not all designed and implemented according to the same template, right? So in addition to humans functioning in the environment, there could be many other machines that are, even if we, pass a regulation saying, everyone has to be solving the assistance game, you'd still have the issue that there are lots of other machines that you didn't design. If we're not careful, they may have kind of strange synergetic feedback loops that cause things to get out of control in ways we don't yet understand. So that's a very important area. If we're going to actually have machines learn more about human preferences, they have to understand that humans are not rational. And therefore, in order to interpret our behavior as expressing or providing evidence about our underlying preferences, we have to know how that expression process works, because we need to invert it, or the machines need to invert it. So in a sense, our machines need to learn inverse psychology, if you like. And that's obviously a very complicated process. There are all kinds of reasons, myopia, emotions, plasticity that cause the expression of preferences in behavior to differ from perfect rationality. And then there are sort of the practical hard work that we need to do to make this actually be the field of AI in the future. If you look at the textbook on AI, every chapter begins by saying, okay, here's how we define such and such kind of problem, right? There's, for example, in the chapter on search, right? There's a goal and a cost function, right? And those are assumed to be given, right? That's sort of what we mean by defining a problem, right? In reinforcement learning, there's a reward function that has to be known for every transition that could possibly take place so that you can supply the reward signal to the learning agent. And so all of those areas of research have to be rebuilt. And it's not, we're not necessarily throwing away all the stuff we've done, because in fact, it's a special case, right? The case of certainty about the objective is a special case of uncertainty about the objective. We're simply saying, no, we need a much broader foundation. And we've only looked at one tiny corner. And the behaviors in that tiny corner are sometimes dangerous and undesirable, and also actually much less interesting, right? They're very single-minded. They don't have incentives to interact with a human, to learn from us, to ask permission. All those kinds of things are behaviors that can't be exhibited in the standard model, at least straightforwardly interpreted. And then we have to show that these methods can actually be successful in the real world. So we have to look at applications like self-driving cars or digital assistants and so on, so that people out there in industry have the confidence to say, okay, yes, we should build systems along these lines, and we should not be following the old approach. So to summarize, if we pursue the standard model to its logical conclusion, as Turing pointed out, we lose control over our own future. If we take this other branch, and I think it's very early to say exactly how things should go, but I'm pretty convinced that this other branch exists, and somewhere down there are solutions that are provably beneficial to humans, and those are the ones we should be doing. In fact, there's ample economic reason to do things this way. These are just better AI systems. And so I don't want people to go away thinking that this is a fight between, the AI ethics people and the AI people, right? That's not going to work, right? What's going to work is AI people understanding that this is just a better way of doing AI, right? Just as bridge builders have learned that, oh, this type of bridge falls down, this other type of bridge doesn't fall down. So this is a better type of bridge, and this is the one we should build, right? And that's a good bridge. That is good civil engineering. And we want this to be thought of as this is good AI. And the other way of doing it, well, that's lazy. We used to do that back in the 2020s, but we don't do that anymore because we know that it doesn't work, right? And that's the kind of mindset that has to happen. So there are other problems arising from AI, misuse, the Dr. Evil problem. So it's sort of cybercrime or cyber war on steroids, which is, and we're not doing particularly well with cybercrime and cyber war right now. So that's more of a societal policing problem. And then overuse, meaning that the human race becomes too dependent on the AI systems that we build. That if they are providing everything and running our civilization, we lose the incentive to know how to do any of those things. And we become dependent and enfeebled. And this is an undesirable future. And a well-designed AI system should actually say, no, we're not doing that stuff for you. You have to keep knowing how to do those things yourself and doing those things yourselves in order to maintain the vigor of your civilization. But we, being myopic humans, may not like that answer and may nonetheless fall into this trap. So there's a lot of work to do there, and that's a cultural and not so much a technical problem. Okay, we have a few minutes left for questions, and then we have time and gather. So thank you very much.
Thanks a lot, Stuart. That was a great talk. I'm hoping everyone's going to keep in mind the distinction between the standard model and the new model. And thanks everyone who's watching for submitting such great questions. I have no delusions that we're going to get through all of them, but I will try to get through as many as we can. So yeah, so the first and most upvoted question that everyone had, Stuart, you can sort of see the philosophy and morality bet coming through. Oh, actually it has changed, never mind. The most upvoted question. Doesn't beneficial AI as maximizing satisfied net human preferences run into the problem of incoherent or evil preferences? Shouldn't it instead seek moral realism and maximize moral goodness?
Interesting question. So incoherent preferences are preferences that can't be satisfied. So in the book, I have a simple example, right? So if there's 3 kinds of pizza, pineapple, sausage, and plain, and you prefer each one to the next. So I prefer pineapple to sausage, sausage to plain, and I prefer plain to pineapple, right? So now I have circular preferences. And whatever pizza the AI system gives me, I say, I don't like that one, I like the next one, right? And this just goes on forever, right? So there's nothing the AI system can do to make you happy. And so all forms of incoherent preference kind of boil down to this, that they can't be satisfied. But if I prefer all 3 of those pizzas to a dinner of licorice, then it's reasonable for the AI system to make me one of the pizzas, but it can't make me the perfect pizza because that doesn't mean anything for me if I'm incoherent about my pizza preferences. So that's one. The evil preferences, to some extent, evil is in the eye of the beholder. And the way that Hassani thinks about this, Hassani is an economist who did the first axiomatic extension of von Neumann-Morgenstern axioms to decision-making on behalf of many people. And he has a social aggregation theorem that under fairly mild assumptions that seem very reasonable, you can show that all Pareto optimal policies will optimize some linear combination of the preferences of the individuals. And then he argues that by fairness or by symmetry, the linear combination should give equal weight to everyone's preferences. So the evil preferences would be the sadistic ones that I mentioned, where if you break down my preferences into preferences about my own well-being, sort of intrinsic well-being preferences, and preferences about the intrinsic well-being of others, if I have a negative weight for the well-being of others, then I am a sadist, right? Because that means I will give up some of my own well-being to hurt other people, right? And he asks, Harsanyi says, look, then that person is simply outside the social contract for which it makes sense to be making decisions on the behalf of those people. And there is no way I'm obliged to help you hurt someone else simply for your own gratification. And so you can zero out, right, at least in the simple mathematical decomposition, you can zero out the negatively altruistic preferences that people have. But I think this whole area of looking at how one's preferences are composed of intrinsic preferences about one's own well-being and preferences about the well-being of other people, I think it's underexplored, and it has significant implications for some of the moral objections to utilitarianism, which to me actually seem incoherent, right? So they seem to have the property that even if no individual in the population has any interest in the well-being of any of the other people, right? The moralist is still imposing some notion of equality that needs to be added to utilitarianism, even though none of the individuals care at all. But of course, if the individuals do care, then utilitarianism does impose, egalitarianism, right? And the optimal resource allocation under pure utilitarianism is completely egalitarian. So I think there's a lot of confusion going on here. As for whether we should simply implement moral goodness, well, I could argue that moral goodness means acting in the best interests of the human race, right? Which is, and you can argue about it, well, how exactly do you calculate that? But that's what I'm trying to implement through preference utilitarianism. And I'm not going to be in the business of saying, well, actually, my preferences, or I am righter about what the future should be like than other people, so I'm implementing my theory of moral goodness. And so this is a preference utilitarianism, incorporates preference autonomy, that everyone is entitled to their own preferences. And it doesn't say that you should care about whether you have anything to eat, doesn't say you should care about how rich you are, doesn't say anything like that. It's what your preferences actually are. The big issue, the place where there's a hole in the theory, I think, is with preference plasticity. And it's not clear. I don't think you can prevent AI systems from modifying the preferences of humans, because almost any form of interaction potentially can modify human preferences. But we don't want the AI system to deliberately manipulate preferences to make them easier to satisfy. So that's an open problem. Good thesis topic. That was a long answer. Sorry, Rohin.
No worries. I think we can get through another question? I don't think that's likely. I will probably just close it at this point. So yeah, thanks again, Stuart, for this session. It's been pretty great. I expect the viewers have gotten a lot out of that. And thank you everyone for coming.